All right, everybody. We're going to start going through these holiday homework problems. I'm just going to kind of solve them all in order. Feel free to jump around to whichever questions you need. You probably don't need all of them. But I'm going to do my best to get through all of them. It'll either be in one or two videos, depending on how much I can get done in this sitting. But yeah, just make sure you use this to check any of your answers or to help you get started on a problem you don't know. Remember, the idea is that you're using this as a resource more than just an assignment. So I really just want you to give a good attempt to all these different questions. I'm not going to care so much that you get them all perfectly right, but you have this resource to go back and kind of check your work and correct anything that you need. Okay. The first section here focuses on a lot of stoichiometry practice, which is really important. So I'm going to start up here at the top. I'm going to balance out my reaction. You can kind of do this trial and error, but the first thing I notice is that I have 5 O's over here and only 2 O's on the left, and I have like an even number and an odd number. So I know that's going to be a bit of an issue down the road. So when I do that, I like to go ahead and start by doubling the odd number to make it an even number. That gives me 10 oxygens over here. And then I can easily get 10 oxygens over here by just making that a 5. And last I have 4 phosphorus, so 4 phosphorus. Right. Then I have a 5.4 gram sample of my phosphorus. So that's my phosphorus reacting with excess oxygen. Okay, excess means I have plenty of O2. I'm not going to run out. Okay. According to this reaction, how many grams of P2O5, my product, are made? All right, like with any stoichiometry problem, if you have information about one of these quantities, you can switch it to any of the other. It doesn't matter if it's a reactant or a product. So I'm going to take my 5.4 grams of phosphorus and do a train track. And I want to know grams of P2O5, so that's what I'll convert it to. Okay, grams of phosphorus on the bottom. Phosphorus is about 31 grams per mole. So I'll write that in there. Mole of phosphorus on bottom. Mole of what I'm looking for, P2O5. On top, put in my mole ratio, 2 to 4. Moles of P2O5, put it on the bottom. Moles of what are grams of P2O5 on top. 1 mole, then I just have to find the molar mass of all this. So 31 times 2 plus 16 times 5, it's like 142. Okay. Multiply everything on top. 5.4 times 2 times 142, divide by 31, divide by 4. 12.4 grams is my answer. B says if 8.2 grams of P2O5 were actually produced. Okay, so this is my calculated amount of P2O5 I should have made. 8.2 grams were actually produced, and I want to know the percent yield. Percent yield. Take your actual number, which will always be smaller than your theoretical, divided by the theoretical, times 100. If you put your numbers in the right spot, then you'll never get a number above 100%. My actual was this 8.2 in the problem, divided by how much I was supposed to make according to the math, times 100. 8.2 divided by 12.4 times 100 give me like 66.1%. All right, so we just have a basic train track for A. Part B is just a percent yield using that information. Part C says what mass of oxygen, okay, oxygen's my other reactant up here, so what mass of oxygen is used to react 5.4 grams of phosphorus to completion? And the wording of this sounds way more difficult than it would be for A, right? This is not like a normal way we would phrase this sort of thing, okay? But the idea is you could do a train track to switch one quantity, grams of phosphorus, to another. And if I do a train track and convert 5.4 grams of phosphorus and convert it to oxygen mass, so grams of oxygen, that'll tell me how many grams of oxygen matches with this much phosphorus. So I'm going to do just that. I'm just going to take my 5.40 grams of phosphorus and turn that into grams of O2. It doesn't matter that they're both reactants. You're just switching from one to another using a train track with a mole ratio. So my 5.4 grams of phosphorus. Again, grams of phosphorus, about 31 grams per mole. Moles of phosphorus on bottom to cancel. Moles of what you're looking for. Oxygen on top. Our numbers from our equation are 5 and 4, respectively. And then 1 mole of O2 on bottom. Convert it back into grams, because that's what the question wants. And you should get a train track set up like that. And then do over math. 5.4 times 5 times 32, divide by 4 and 31. It's 6.97 grams of O2. Okay. That means that's how much O2 I needed to fully react with this much phosphorus. Now in this problem, it said we had excess oxygen, so I would have had more than that. If a problem would have phrased like, I have 10 grams of oxygen to start, I could also find how much is left over, how much excess oxygen I have by like subtracting these. But that's not what we're asking for here, we're just looking for this number. All right, number 2, solid aluminum wire. Okay. The fact that it's a wire doesn't matter, but I just have some aluminum and it's telling me it's a solid. Was added to copper 2 nitrate. Now the problem didn't tell me what that is, so I need to figure out what that compound is. So I'm going to take my copper 2, should be this copper 2 plus, and mix it with a nitrate, NO3 minus. I swap my charges, the 2 goes to the nitrate, so I'll have 2 nitrate molecules. The 1 goes to the copper, and I should make the compound CuNO3 2. Okay, so solid aluminum is added to this thing, copper 2 nitrate. Solid copper and aluminum nitrate were produced. So the problem didn't have to do this, but it gave us the products as well. So these things are kind of what we started with. This is our initial step. And then we have our products. It told us we have solid copper and then some aluminum nitrate were produced. And we just want to write the balanced equation. It says, don't forget states of matter. So we can kind of go back to what we were talking about, copper 2 nitrate here. It has a nitrate, so I know this is aqueous. So I can start the reaction with my 2 reactants. I already know their states of matter. And we can write what they produce. Well, it told us solid copper first. It's just copper by itself as a solid. And this other compound, aluminum nitrate. So aluminum nitrate, again, write both of my charges. Swap the charges, so the 3 goes to the nitrate, the 1 goes to the aluminum, and it just makes some AlNO3, 3. Its state of matter, again, it has nitrate in it, so it's probably aqueous. That's my unbalanced reaction. Now I just need to balance it real quick. I just need to focus on these nitrates because those are the only things not balanced. I have 2 of them over here, 3 of them over here, so I need to kind of make a common factor, and the easiest common factor is 6. So if I put a 3 here, I have 6 nitrates here, 6 nitrates here, and then let me just balance out the rest. 2 aluminums, give me 2 aluminums here, and then 3 coppers, give me 3 coppers here. Okay, and then question 3 is related to this last question. We're using this balanced reaction. If 50 milliliters of 0.1 molar copper nitrate. Okay, so just this first part, this is my volume and my molarity, my capital M, of copper nitrate, which is this chemical here. Okay, we usually don't write it like this. Usually in a reaction, I'd give you grams or moles, but we have molarity and volume. We can use that to find moles using the molarity as moles per liter. Okay, so that's something we've done a couple of times, but maybe not in this exact context. So I have this much copper nitrate was used with excess aluminum. That means I'm going to add some solid aluminum, but I'm going to add so much that I don't even have to worry about it for the math. I'm definitely going to run out of copper nitrate first. Okay, so that's good. How many grams of solid copper was produced? So I'm looking for grams of copper. And then the second question says how many moles of aluminum nitrate were produced. So I have 2 separate questions that are looking for different things. Both of them going to solve the same way. They're just a train track. All right, so I'm going to start with my copper nitrate. First thing I'm going to do is get it into moles. I can't use anything with this molar or this milliliter, so I'm just going to solve the molarity formula. Molarity is moles per liter. My molarity is 0.1. My liters, make sure to convert milliliters into liters, divide it by 1,000 to get 0.05. 0.05 times 0.1, add an extra 0, you get 0.005 moles of your copper nitrate. And then we could do both for our different problems here. So to organize it, I'm going to call this first one part A. And I'm going to take my 0.005 moles of copper nitrate, CuNO3 2. Do a train track. I'm going to start by turning it into grams of copper. So I'm going to do my mole to mole ratio. We have this equation from the previous problem. Both these are 3's, so I just put my 3 to 3 ratio there. And then turn it into grams, 1 mole of copper. Go to your periodic table, copper. 63.5. You can write 63.5 to be more accurate, or round it up to 64. It don't matter. Just keep it as simple as possible, or round it up to 64. That'll give me the answer to my first problem here. So let's just quickly 0.005 times 3 times 64 divided by 3. I'm going to write it up here. 0.23 grams of copper for the first part. And then second problem, how many moles of aluminum nitrate were produced? I'm just going to repeat the problem, but just look for a different thing. So I'm going to start it off the same with my 0.005 moles of copper nitrate, then do my mole to mole ratio. I'm looking for aluminum nitrate. Oops, which is a 3, but all right, I have a 3 to 2 ratio this time. So 2 on top, 3 on bottom. So I'm just going to take my 0.005 times 2/3. Okay, and then I'll get my answer for the second part here, 0.00333 grams of aluminum nitrate. On the back of this first page, next question is a simple one. Nitrogen gas and hydrogen gas are combined to make NH3. Write a balanced equation. So I have nitrogen. It is a gas. It's not bonded to anything else. So I need to remember that nitrogen is one of our diatomic molecules. So nitrogen gas implies it's by itself. So it's just an N2. Hydrogen gas, same thing. Hydrogen gas is H2. They combine to make NH3 ammonia. So N2, H2, combine to make NH3. And now I just need to balance it. I have the same sort of common thing you see a lot. 3 hydrogens, 2 hydrogens. I need to find a common factor. Make them both 6. 6 hydrogens, 6 hydrogens. Nitrogens worked out to balance. That's our balanced reaction for making ammonia. Number 5. If 10 grams of nitrogen react with 10 grams of hydrogen, how many grams of NH3 should be made? So this is a little bit more complicated than the front page because now I don't know what thing is going to run out first. Okay, so I have 1 reactant, 2 reactants. Our strategy here is to either find out which one runs out first by converting both of them into moles and seeing which one you have less of, finding the limiting reactant, or the alternative strategy, which I think is a little bit more efficient, is just doing the problem twice and circling the smaller answer. Whichever one produces less grams of NH3 would have been the one that ran out first. The one that kept producing didn't take into the fact that one of those things has already run out. Okay? Both of your answers will be how many grams of NH3 you would have made if all of your reactant was able to be used. Okay? But not all your reactant will be able to be used for your excess thing, because some of it will still be left over. So I'm going to take my 2 train tracks, 10 grams of N2, 10 grams of H2, and just solve. So grams of N2, nitrogen weighs 14, so this is 28 grams of N2 per mole. Make sure to use my balanced equation up here to know 1 mole of N2 equals 2 moles of NH3. And then convert, we're looking for grams of NH3, so we'll do one more step. NH3 weighs about 17 grams. Right, I'm just going to go ahead and set up the bottom one before I get my calculator out. It's going to be basically the same, except this number will be different. 1 mole of H2 weighs 2 grams. My mole ratio will be a little bit different because I'm looking at H2 instead. 2 moles of NH3 are made from every 3 moles of H2. But this last step should be the same. All right. And then I'm going to take up my calculator and solve each of them. All right, so the first one here, I have 10 times 2 times 17 divided by 28. And if I'm able to use up all of this nitrogen, it'll make me 12.1 grams of NH3. For my hydrogen, 10 times 2 times 17 divided by 2 divided by 3. If I'm able to consume all of this hydrogen, it'll make 56.7 grams of hydrogen. Now, that would be nice, but I don't have enough nitrogen to do that. This is my smallest answer, so I circle it, meaning nitrogen was my limiting reactant. Okay, and question 6 says, how many grams of leftover H2 would you have after this reaction went to completion? So clearly, I wasn't able to use all my hydrogen. It was my excess reactant, my ER. So exactly how much do I have left after the reaction finished? All right, so I kind of need to do like what we did on the front of the page here. So I used 10 grams of nitrogen, and that used some amount of hydrogen, but I don't know exactly how much. So I'm going to do a train track. 28 grams of nitrogen, turn it to moles to compare. And then I'm going to convert moles of nitrogen into hydrogen. So moles of nitrogen, moles of hydrogen. And I'm doing this because I want to find out how much hydrogen I needed to react fully with all of this amount of nitrogen. All right, my numbers here, hydrogen's a 3, nitrogen's a 1. My last step, moles of hydrogen on bottom, grams of hydrogen on top, 2 grams per mole. All right, now let's solve this train track. I guess give me 10 times 3 times 2, divide by 28. Is 2.14 grams of hydrogen. This number means this is how much hydrogen you need to fully react to pair with all of that nitrogen. But that's not my answer, because I want to know how much H2 I would have left after this reaction finished. And in the previous problem, it told us we started with 10 grams of hydrogen. I needed 2.14 of it to react with my nitrogen fully, and everything I have left over, my 7.86 grams of hydrogen left over, would be my excess amount of hydrogen. Right? Similar sort of problem here for 7. I have a more complicated looking reaction. It says, how many grams of NAF form? Okay, so I'm looking for grams of NAF when 0.5 moles of Fe, or HF is what that does say. So I have 0.5 moles of this. React with excess of this NaSiO3. So I have plenty of this. So I don't have to do a limiting reactant thing. That's good. I'm just going to take 0.5 moles of HF and do a train track to convert it into NAF. So I have 0.5 moles HF. And so let's go ahead and go through solving it. So this is moles of HF on bottom. And I'm looking for NAF, so I'll put moles of NAF on top. And then I go to my equation, 8 HFs make 2 NAFs. And then I need grams, so I'll go 1 mole of NAF on bottom and figure out how many grams of NAF that is on top. All right. So on my table, I have Na over here weighs 23, F weighs about 19, and add that together, and I get like 42. 42 grams of NaF. And now I'm ready to solve. 0.5 times 2 times 42 divided by 8. .25 grams of NaF. Cool. The second question here says how many grams of Na2SiO3 can react with 0.8 grams of HF? Okay, so this is kind of like what we just did up here in number 6. Just saying, I want to know how much of this reactant I would need to fully react all of this. So it's another way to phrase a stoichiometry problem, but we're essentially doing the same thing. If I just convert this into grams of this, that's what it's telling me. It's telling me how much of this do I need to match with this. So I'm going to do exactly that. I'm going to take my 0.8 grams of HF and just do a full train track and convert it to the other thing I'm looking for. Grams of HF, moles of HF on top. Hydrogen's 1, fluorine's like 19, so that weighs about 20. Moles of HF on bottom. Moles of what I'm looking for, which is this Na2SiO3 on top. And then I go to my balanced equation, 8 of these, only 1 of these. And then moles of this on the bottom to cancel. Convert it to grams on top. 1 mole of these weighs, that's a lot to add up, so let's just go ahead and do that. I have Na2, which is 23 times 2, plus silicone over here on the right is about 28, plus oxygen times 3 would be 48. Gives me 122. Okay, let's solve. Take my 122 I just got, times 0.8, divide by 20, divide by 8. Okay. 0.61 grams of Na2SiO3. Next question here is more of the same. The following reaction produces 2 compounds that are commercially useful. Who cares? Gives you the compounds. S2Cl2 and SF4. My reaction already gave it to me, that's nice. And then it says if you began with 16.3 grams of sulfur dichloride. Okay, sulfur dichloride. It doesn't tell me which one that is, but I can probably figure out this is a sulfur and 2 chlorines. So this is my sulfur dichloride. And 10.5 grams of sodium fluoride. That's sodium and fluorine together. So that's sodium fluoride. What mass of sulfur tetrafluoride? Okay, this is a sulfur, and tetra means 4 fluorines. So we're looking at this product can be produced. So I have my 2 different numbers here. I need to find how much my product I make. So this is like a limiting reactant problem again. I'm going to do it the same way where I just take both of my quantities, SCl2 and 10.5 grams of NaF, and I'm just going to convert both of these into product and see how much they make. So on top here, I need grams of SCl2 converted to moles of SCl2. 1 mole, that weighs be like 32 plus Cl is about 35.5. And I'll add that twice. It's something like 103. If you got 102 or if you wrote the full number, it won't change your answer that much. It doesn't really matter. Moles of SCl2 on bottom, moles of what I'm looking for, SF4 on top. Now my 1 for these, but I have a 3 over here. So my 1-to-3 ratio, I'll write that in. Moles of SF4 on bottom, turn it to grams of SF4 on top. F weighs about 19. We have 4 of those, plus 32 grams for S. Gives me 108 grams per mole. All right, on the bottom down here, I'm going to turn grams of NaF into moles. One of these weighs, that's 23 plus 19 again, 42. Moles of NaF oops, I'm looking for SF4. All right, my ratio this time, 4 moles of NAF makes just 1 mole of SF4. Okay, mole of SF4 on bottom, and again, just like on the top, it weighs 108 grams. All right, so those should be my 2 train tracks. The smaller answer is the right one. So the top, 16.3 times 108 divided by 103 divided by 3, 5.70 is what I'll round that to, grams of SF4. On the bottom, I got some 10.5 times 108, divide by 42, divide by 4. That's really close, but that gives me 6.75 grams of SF4. Between those two, this is my smaller number. Make sure to circle that one as your answer. I ran out of SCl2 first. Part B asks how many grams of excess reagent, which would be this NAF, how much of that excess is left after the reaction. We're going to do that same sort of process again. I had 16.3 grams of SCl2. I want to see how much NAF I needed to react with that. So fortunately, I could just kind of copy some of the numbers, which is nice. 103 grams of SCl2 per mole. Do my train track. Moles of SCl2 is 3. Turn it into moles of what I'm looking for, which is my excess reactant NAF. I use 4 moles of that. 1 mole of NAF weighs about 42 grams. And I'll solve this train track. 16.3 times 4 times 42, divide by 103, divide by 3. I get 8.86 grams of NAF. So that's how much NAF I needed to fully use up all of my SCl2. And if I go back to my previous problem, I had 10.5 grams of this to start. That's a nice way to check your work. This number should always be smaller than what you started with because you didn't quite use all of it up. So then you just subtract 10.5 minus 8.86 to get your 1.64 grams of NAF in excess. Number 9, I rewrote it here just so it's a little bit bigger. It wants me to balance the predict the products, balance the reactions, and write in the state of matter signs. All right, so I have my first one, BaCl2, NaCO3. This is just a classic double replacement. So 2 different ways you can think about it. You can think about like swapping the 2 nonmetals with each other or swapping the 2 metals. Or you can kind of think about the first and last thing will bond together and the first thing over here and the second thing over here will bond together. Either of those methods mean the same thing, really. I kind of think about it like this usually in my head. I think Ba, the first thing, and the fourth thing, carbonate, will go together. And then the third thing and the second thing kind of go together. But either way you want to do it. The important thing is when you predict the products, you have to make sure you're not just copying numbers from over here. You have to make those numbers again. So over here you have barium, something with barium, which has a 2+ charge. Something with carbonate, which has a 2- charge. Fortunately, this time you have the same charge. So they do just cancel out to make BaCO3. Its state of matter, it doesn't have any of those special things that would make it soluble, so I'm going to assume this is a solid. And same thing with this one, but this one has Na, so it's aqueous. So you started with a solid and something aqueous. Your first product is barium carbonate, solid. And then NaCl. Okay, I know what those charges are. That one's pretty simple. NaCl, which is also aqueous. All right, for part B, I have aluminum sulfate. This doesn't have any of those things, so I would assume it's a solid. H3PO4. Okay. A little bit different, and I don't know if we've really done a lot of this yet. This is an acid. It starts with an H, like this. All acids are aqueous, but we haven't really learned that yet, how to do their states of matter. But just so you know, all acids and all bases are always aqueous. So that's like how you would figure that out. Again, though, you have this sort of salt and this acid. It's a double replacement, so I'm going to do the same thing. Okay? The aluminum and the phosphate. Aluminum's charge is a 3 plus. Phosphate's charge is a 3 minus. So those combine nicely just to make AlPO4. That is a solid because it doesn't have any of the things that would make it otherwise. Then hydrogen and sulfate. Hydrogen's charge would be like a 1 plus. Sulfate's charge is a 2 minus. If you don't remember, that's where the reason there's a 2 over here, it came from its charge. So sulfate is a 2 minus, so you have H1 plus, SO4 2 minus, makes H2 SO4. Okay, it gets H is 1 plus, SO4 is 2 minus, swap the charges. H2SO4 is another acid, so it is aqueous. Part C, here you have kind of the same sort of situation. You have HNO3. This is an acid. It starts with an H, so it's aqueous. NaCl has Na, so it's aqueous. What I kind of forgot to do in these last two real quick, so let me go back and change it, is balancing them. So if you're watching this out of order, I'm sorry, but I need a 2 here, and everything else is good. The second one here, also not balanced, so let me just quickly do that. I have 3 sulfates, so I probably need a 3 here, and then I need a 2 here to make the H's match, and then I need a 2 here. So yeah, that's what those answers should be. Okay, part C, double replacement, H and Cl will bond together. 1 plus and 1 minus, so they just make HCl. That's an acid. Call it aqueous. The Na and NO3 bond together. Na is 1 plus, NO3 is 1 minus, so that those work out nicely as well. Make NaNO3. It has things that would make it aqueous. Remember, your 4 things that make something aqueous are your sodium, potassium, nitrate, and ammonium. NH4 plus. Number 4, it has that ammonium. It is aqueous. Barium hydroxide ends in an OH. That tells you it's a base. Bases are aqueous. All right. NH4 goes with the OH over here. Ba will go with the Cl. Okay. And whenever you're reacting things with OH, they always end up looking a little bit ugly. But in this case, it actually works out okay. NH4 is a plus charge. OH is a minus charge. So their charges are nice, so they just work out nicely to make NH4OH. And you would write it fully out like this. You wouldn't like combine the H's or anything. You want to show that like this ion NH4 is there and OH is there. Because those things would be aqueous in solution, so they'd kind of like fall apart. And then over here, barium and Cl. Barium is Ba2 plus, Cl has a minus to make BaCl2. That's a solid. It doesn't have any of those 4. All right, to balance these real quick, I need a 2 over here, my hydroxides and hydroxides. That throws off my NH4s though, my ammoniums. So let me add 1 over here. Then I have 2 chlorines to match those 2 chlorines. That should be good. All right, down here, part E, I have silver chlorate, ClO3 is a polyatomic, and some nickel nitrate. First of all, this must be a solid because it doesn't contain my magic things here. And this must be aqueous. Ag and NO3 bond together. Ag is silver, 1 plus. NO3 is 1 minus. So that makes AgNO3. Contains nitrate. It is aqueous. My nickel. Nickel, we don't know its oxidation state readily, but we can figure it out what it was over here. It'll be the same on the right side. So when nickel combined with nitrate, remember nitrate has that minus charge, it gave it 2, which implies nickel has a 2 plus charge. So nickel is 2 plus, combining with this chlorate. You can kind of do the same test over here if you don't remember. Chlorate has a minus charge. Okay, it didn't give any numbers to silver, so it must have just been a 1 minus. That makes nickel chlorate. 2. Kind of ran out of room. This doesn't have any special things, so we'll call it solid. All right, throw a 2 here, throw a 2 here. Everything else looks good. Okay. And just as a last little follow-up to that last question, we have number 10. Label these as soluble or insoluble. Barium phosphate, it doesn't contain any of those things, so I'd expect it to be a solid. NH4NO3 contains 2 different things that would make it, this labeling system was stupid, that's my bad. Soluble or insoluble. Soluble means it dissolves, and I had you label that with an S. So that's kind of stupid. I should have had you label it with aqueous. Insoluble should be an S. So like that's just a dumb labeling system there. That's not my fault. So I'll first label them all with just these normal symbols we use. So this would be a solid, okay? But in this case, it'd be insoluble. This one would normally dissolve, so it'd be soluble. So I would normally call this like AQ, but in this problem, it would be S. This one, K, has a K, so this would dissolve. It would be aqueous. So that's something that dissolves. It would be soluble. FeCl3 doesn't contain any of these things, so it will not dissolve. Normally, I would call this a solid. For the context of this problem, it's insoluble then. And then PbCl2 doesn't contain any of those special things, so it would also be solid. Solid. So insoluble. So however you label, that's fine. I would pick one or the other. The ones in parentheses or not. Either way is fine. I know what you mean. All right. 11, we have a couple net ionic reactions to write. So first thing I'm going to have to do is kind of rewrite this with the state of matter symbols. So my Na2CO3 has Na, which would make it aqueous. Calcium nitrate has nitrate, so I'm going to think it's aqueous. That produces some NaNO3, 2 of them. Definitely aqueous, has 2 things that would make it aqueous, leaving us with some CaCO3 solid. My net ionic reaction, they're going to split apart into their ions. This one was already balanced for us, which is nice. So now I'm just going to split everything apart. I have 2 sodium ions. I write the 2 in the front because these things are ions. They're not attached to each other anymore. They're kind of free floating independent. So I have 2 separate ions, so I write it in front like that. Plus a CO3 2- ion. Plus a calcium 2+ ion. And 2 nitrates. So the left side, those things are all aqueous, so they all split apart into those ions. Those ions are free to go around, react as they want. They're no longer attached to their initial thing. Over here, I have 2 sodiums and 2 nitrates. And this solid at the end will stay together. This is called the complete ionic equation. And then it also wants me to write the net ionic. So I'm going to take the same equation, but just leave out any of the spectator ions. Any of the things that are the same on both sides, get rid of those. They don't actually participate in the reaction, they're just watching. So they're called spectators. Rewrite it without those to get the net ionic. This is the actual reaction occurring in our reaction here. All right, next question makes it a little bit more difficult. I have the reaction of potassium chloride and lead 2, should be in parentheses, nitrate. All right, first thing I need to do is write both of my products. I have potassium chloride. So potassium's a 1+ charge, chlorine is a 1+ charge, so this just makes regular KCl. It has a K, so it's aqueous. Lead 2 nitrate. Lead 2, telling you this is lead with a 2+ charge. Nitrate has a 1- charge, so when we swap those, Pb, lead, just gets the 1 from nitrate, but nitrate gets a 2 from lead. This has a nitrate, so it's aqueous. All right, I have to predict the products as well. So the first and last thing will pair together, this metal and this non-metal, K and O3. Both have just a 1 charge, so they just make a 1-to-1 ratio to make K and O3, which is aqueous. Pb, which had a 2+ charge still, combines with Cl, which has a 1 minus charge, to make PbCl2 solid. Balance my reaction. I need to add a 2 to my potassium nitrate and a 2 to my potassium chloride. Then everything is balanced. That's my molecular equation. I'm going to write my ionic by splitting apart my aqueous things into their ions. 2K plus, 2Cl minus, Pb2 plus, 2 nitrate ions, 2K pluses, 2 nitrates, and my lead 2 chloride doesn't change. That's the second part there. That is my complete ionic equation. This time I have some potassium and some nitrate. Cancel those out to write my net ionic equation. Like that. Part C. Sodium chloride is NaCl. That's aqueous. And again, lead 2 nitrate. PbNO3, 2. Aqueous. This is going to look very similar to the last one, so I'm just going to kind of speed through this one. NaNO3, aqueous, PbCl2, solid. Balance it, 2, NO2. And this is pretty much the exact same problem. 2 Na pluses, 2 Cl minuses, Pb2 plus, 2 nitrates, 2 sodium pluses, 2 nitrates, some lead, 2 chloride. Cancel out my spectator ions. Write your net ionic equation. And then my last one here, part D, sodium carbonate. Sodium is Na, has a 1 plus charge. Carbonate is CO3 2 minus, so its 2 goes over to the sodium. This has sodium, which is aqueous. Iron 2 chloride is FeCl2. That is a solid because it doesn't contain one of those 4 compounds. NaCl bond together. That's aqueous. Fe2 plus and carbonate. Both of those have a 2 plus and 2 minus charge, so they just combine at a 1-to-1 ratio, and they make another solid. Balance my equation by putting a 2 here. Everything else looks good. And then split apart my aqueous things only. Keep this FeCl2 solid. Split this apart. And keep this FeCO3 solid. My only spectator ion this time is my sodium. I'm left with CO3 2 minus plus FeCl2 solid gives you 2 Cl minus and FeCO3 solid. Cool. These are redox reactions. Okay. Both of these are asking the change in oxidation number for my copper. So oxidation number, remember, if anything is ever by itself, meaning it's not bonded to any other type of atom, its oxidation number is 0. So Cu starts at, that's a 0, not a 6. And at the end, it's bonded to copper nitrate. Copper nitrate is just a normal binary ionic compound, meaning users use their normal oxidation states. Right, the 2 came from copper up here, was a 2 plus. Copper nitrate is just like a normal compound you should have known how to write before we even get into the complicated rules. Okay, silver goes from silver nitrate, sort of the same thing. Nitrate's charge is -1, so silver was 1 plus. And silver's by itself over here, so it's a 0. The element that is oxidized is the one that loses electrons. Lose electrons, oxidation. Losing electrons means if you're losing a negative, you get more positively charged, which would make that copper. Copper lost electrons to get more positive. The element that is reduced, gain electrons reduction. If you're gaining electrons, you're getting more negative. 1 to 0 is subtracting, that's getting more negative. So silver is my reduced element. All right, this one, zinc by itself, starts as 0. Makes zinc sulfate. Zinc sulfate here, SO4 has a charge of 2 minus. Zinc is 2 plus. So it goes from 0 to 2 plus, meaning it is oxidized. H goes from this compound. SO4 is 2 minus. H is 1 plus because there's 2 of them. It has a total 2 plus, but each hydrogen is 1 plus. So hydrogen starts, each individual hydrogen atom starts at a 1 plus charge over here. And at the end, it's just H2, which means it goes down to 0. Hydrogen is reduced from having a 1 plus charge on the left to a 0 charge on the right. And here in 14, a little bit different. I want to give the oxidation number of each element. So I can use kind of the same trick to find copper. PO4 phosphate normally has a 3 minus charge, but that applies to the whole compound. So that doesn't actually give me any of the answers here, because this time I want to know each individual element. But I can use that to help me find coppers. Each phosphate has a 3 minus charge, and there's 2 of them, so it has a 6 minus charge overall, meaning this copper must cancel it out and have a 6 plus charge overall. There are 3 of them total, so each one of those coppers has a 2 plus charge. If each copper has a 2 plus, it cancels the total charge of 6 negative from the phosphate. And then I have to break down the phosphate. The PO4 has a total charge of 3 minus, but I have to figure out where that 3 minus comes from. Oxygen always has its oxidation state of minus 2. There's 4 of them, so it equals a total of minus 8. So I can use that to figure out what number phosphorus must be to cancel out with minus 8 and equal negative 3, which is 5 plus. 5 plus negative 8 equals negative 3. All right, then we get on to some mixed review stuff. 15 here, we're drawing some Lewis structures, and then predicting the VSEPR shapes. SF6, okay, I need to go back to my periodic table here. I need to write how many valence electrons everything has. Sulfur has 6, fluorine has 7 times 6, so this is 42 plus 6, 48. I can use 48 electrons in my drawing. S will go in the middle. My 6 Fs will go all the way around. Draw a line to each one. Add electrons until everything's valence is full. Okay, everything is satisfied. Fluorines each have 8 electrons, which is perfect. Sulfur currently has 12, but that's okay. Sulfur can have anywhere from 8 to 12 and be satisfied. So I just need to make sure we use 48 electrons. Each of these arms uses 8 times 6 is 48. That's my drawing. Its VSEPR shape has 6 bonding groups and 0 lone pairs, making it octahedral. Part B, I have SiO2. Okay, so first of all, silicon has 4 electrons. This is 6 times 2 is 12. My drawing can only have a total of 16 electrons. Silicon is my first element, put it in the middle. Spread out my 2 O's. Add lone pairs until everything is happy. Everything is satisfied with their 8 electrons, but I don't think I only use 16. If I count it, I use 20. So I need to save 4 electrons, so I'm going to make 2 sets of double or triple bonds. I'm going to make 1 double bond over here, so I'll get rid of 1 lone pair here and 1 lone pair here. Place it with a bond. I'll do the same on the other side, get 1 lone pair here, 1 lone pair here, replace it with a bond. And I'm just going to redraw it for clarity. I should have something that looks like this. This is kind of like a straight line, which kind of gives away that it's linear. You also could have chosen to draw it something like this. a triple bond on one side and a double bond on the other. And that's fine, but this version is actually better because we know about things like formal charges now. If I find the formal charges of all these atoms, oxygen's supposed to have 6, and it has 1, 2, 3, 4, 5, 6. It's a charge of 0. And so does this oxygen. Silicon's supposed to have 4 things touching it, and it has 4 lines and no lone pairs, so it's 0 as well. Everything in this picture has a 0 formal charge, which is better than this one. In this picture, this oxygen would have a -1, this one would have a +1. And for that reason, that's why this is the preferred Lewis structure. So for C, I have pH3. P has 5 plus 3 is 8 electrons. P in the middle, my 3 H's. Add lone pairs until everything's happy. Hydrogen doesn't need any, so just my phosphorus. Okay, and I have my 3 H's, everything's good. I used 8 electrons, my drawing checks out. I have to get the name of the shape. I have 3 bonds and 1 lone pairs. If there were all 4 bonds, it'd be tetrahedral, but they're not. So this is trigonal pyramidal. All right, and then D down here says 4 plus 6 times 3, and the 2 negative means I have to add 2. So my drawing here has 24 electrons. Wait, yeah, 24. I'm going to draw it over here. CO3, 2 minus, C in the middle, each of my O's spread out. Make everything happy by adding some lone pairs. If I count my electrons, I use 26. I need to save 2. Doesn't matter which arm you pick. I'll pick the bottom one for symmetry. Make a double bond. That saves my 2 electrons, brings me down to 24. My drawing is good. It has a charge though, so just make sure to put the whole thing in brackets with its charge in the upper right corner. All right, 16. Below are the first ionization energies. Ionization energy is how much energy it takes to lose an electron. Okay. A high ionization energy implies it takes a lot of energy to remove an electron, meaning you hang on to them pretty tightly. So if I'm comparing my group 2 elements here, beryllium to radon, radium, I don't know, whichever one it is. Beryllium has the highest ionization energy, meaning it'd be the hardest one to get rid of an electron from, of these. And same thing down here. It seems like it gets harder to remove them as you go to the right. Fluorine has a really high ionization energy. Okay. Question A says, explain the trend in ionization energy of the alkaline metals. So, alkaline metals are these, and the trend to me goes 899, 737, 590, 549, 503, 609. Overall, it goes down. Like, it goes up a little bit at some points, but it mostly goes down. So that would be explaining the general trend. Ionization energy, which I'll abbreviate IE, decreases as you go down the alkaline earth metals. Okay, now to explain it, so this is just kind of our trend, i.e. decreases as you go down. That's what the numbers there say. But to explain it, the main thing happening as you go down, we look at these elements, it's all of these in the second row. Okay, we're going down a column here, and as you go down a column, things get bigger. Okay, so as the atoms get bigger, or it could be better. See, as the atomic radius increases, a little bit more concise. As the atomic radius increases, it becomes easier to remove electrons since they are further from the nucleus. Ionization energy decreases as you go down the alkaline earth metals. So that's the first part. I would give you 1 out of 2 points on the question if you told me that. The second part is actually explaining it. So it's to explain the general trend. So it's describing why it actually happens. Okay. As the atomic radius increases, those atoms are getting bigger. It becomes easier to remove electrons since they are further from the nucleus. And there's a couple different ways you could say that, but I think that's a pretty concise way. You could also mention Coulomb forces, positive and negative charges, something like that. You could draw a little picture displaying this as well. Any of those would be valid ways to answer the question to get that second point. Part B, we're doing essentially the same thing. Describe the general trend in ionization energy for the period 2 elements. Okay. Now for me, this just says to describe it. So I don't really have to explain it this time like I did in the previous time. I will for practice, but for this one, I would make this one only worth 1 point for you. And all you have to do in this case is just tell me why it goes up, or just tell me that it goes up. You could say ionization energy increases as you go to the right in period 2. Okay. And for me, that would be a 1 out of 1 point question. As long as you said that, that would be all you actually need to say. I'm going to explain it just for practice. Okay? To explain it, it's kind of the same idea. There's 2 different ways I would explain it. You could say basically this exact same thing, but backwards. You could say as the atomic radius decreases, it becomes harder to remove electrons. Okay? Because as you go to the right on the table, they're actually getting smaller. Or you could talk about the effective nuclear charge, saying the effective nuclear charge increases as you go to the right, making it harder to remove electrons. Because we just wrote this one up here, I'm going to write this other example of effective nuclear charge at the bottom. As Z effective increases, it takes more energy to remove electrons. If you get to a problem like this, you're not exactly sure how much detail you should put, it doesn't hurt if you have the time to include like a sentence like this. That would not hurt you from the problem and make sure you get all the points that you're looking for the problem. Right, we have a continuation, part C of number 16. It says to explain why the ionization energy for oxygen is lower than the ionization energy for nitrogen. So, bring those numbers back up. They're on the back. Cool. Okay. So we have oxygen and nitrogen. They're right next to each other. Okay. So my trend normally goes up as you go to the right, but there's a bit of a weird dip down here. So the trend is like mostly going up, goes down a little bit, and keeps going up. So it's trying to say why is this trend the way it is there. Okay. So explaining and reasoning why the ionization energy for oxygen is lower than nitrogen. According to our trend, it should be higher. All right, so it's a little bit weird for this situation. So what you need to do for a problem like this, and I think this is probably more advanced than we really need, but it's something I could hypothetically see popping up. So I'm just going to kind of show you. Oxygen, I'm going to draw its orbital diagram. 1s2, 2s2, 2p4. It'll look like this. Whereas nitrogen is 1s2, 2s2, 2p3. Okay. And what's it's saying here is it's actually harder to remove nitrogen's electron than it is for oxygen. Oxygen's is easier to remove. Even though oxygen is a little bit smaller, right? And nitrogen's a little bit bigger. You would expect it to be opposite. For some reason, this electron's easier to remove than this electron. And it has to do with something called the stability of half shell. Okay. So that's not my answer. I'm just kind of writing it down to talk about it. All right. Nitrogen has a half full 2p orbital. It is exactly 50% full. Okay. It is optimal for it to be empty or to be completely full. But it's kind of like if it's half full, it's a little bit more stable than other arrangements. Okay. So it would kind of go like something like this. Having 0 or having 6 would be like the most stable. Okay. And having 1 or 2 would be really bad, or having 4 or 5 are really bad. But having 3, having exactly in the middle is like kind of okay. It's kind of stable. It's like a way to explain it. So like the overall stability is you either want 0 or 6, but having 3 being right in the middle, having half full, is like kind of a way to be half stable. And you can think about it, each of these electrons, this is a little bit more symmetric. Each of these orbitals here have one of their 2 electrons in them, so it's like kind of balanced. And we like to think about like the fan blade sort of thing as our symbolism for this. Imagine something had 3 blades. Okay. And if you have an unequal weight on each of those 3 blades, then your fan's not going to work very well. So something like this over here, this would be like 1 blade that weighs 2, and then 2 that weigh 1, and that'd be kind of unbalanced. But in this case, all 3 of your blades weigh 1, or have 1 electron on them. So as the electrons spin around, you have an equal amount everywhere, which is like a little bit stable. All of this to say, it's a little bit more complicated than this, but this is just kind of our explanation. This electron is easier to remove because it would make you have a half full subshell. And that's the answer to this, which is kind of annoying. This electron is easier to remove. Oxygen's outermost electron is easier to remove because it makes a half full it makes a half full subshell. Cool. Part D says hypothesize the approximate value of the second ionization energy of lithium. The second ionization energy is the energy to remove 2 electrons. The first one and then the second one. We go back to lithium. Lithium's first ionization energy is 520. Okay. And we're just trying to estimate what is the second ionization energy. All right. What we need to do is look at lithium's electron configuration and kind of think, is there going to be a significant difference between removing the first and second valence electron? This first electron is a valence electron. When I remove this, it takes 520 energy to remove that electron. Okay? But my second electron I need to remove is on a further down shell. Right? The first one is on the 2s orbital, is a valence electron. These 2 electrons are core electrons. And it takes a lot more energy to remove a core electron than it does a regular valence electron. So you should see a significant spike in energy for the second ionization energy of lithium. Because it only has 1 valence electron, losing its second one would take a lot more energy. I usually like to guess like 10x energy to remove a core electron than to remove a valence. So I would guess 5,000. Okay. That would be my guess, and my justification would be lithium's second electron is a core electron. And that'd be my answer. Your answer could be any like huge range, probably anything from like 1,500 to like 10,000, as long as you justified why. And it's mainly this idea that second electron's much harder to remove, so there should be a spike in ionization energy. All right, number 17, we have a PES spectrum, which are always my favorite because I think they're easy. Consider the PES spectrum for an element shown below. Scale is logarithmic and represents the binding energies of electrons in megajoules per mole. Doesn't matter, that's just how these always are. We have a logarithmic scale down here, sure. Binding energy increases right to left, so the most tightly bound electron is at the far left. So it's telling us this is our innermost electron, which we already know, but it's just telling you this is a normal PES spectrum. We want to identify the element and write its electron configuration. Remember, this always just follows the same order as every other electron configuration. The height of the peak corresponds to how many electrons. So this one and this one have 2. This one has 6. This is 3s2, 3p. On the last peak, it may or may not be completely full, so we have to kind of estimate how many electrons we think it has based on the height of the others. To me, it looks like it's about double the height of this one. So I'm going to estimate this has 4 electrons. So its full configuration would end in 3p4. So if I go to identify that element, 3p4, this is 3p, it'd be sulfur. Part B says how many unpaired electron spins does the element have? Okay, so I'm going to rewrite its configuration as an orbital diagram to check that. So I'm basically just rewriting their exponents and just drawing out the electrons instead of just writing the number. And everything else is full, but when we get to 3p4, the order we put them in is important. Always fill up all the lines first, and then go back to the first and refill them in. Unpaired electron spins mean there's only 1 electron in that box, which there are 2 unpaired electron spins. This box and this box. This element forms a compound with chlorine. Write the most likely formula for the compound the 2 elements will form. So we have S and Cl bonding together. All right, and we have to kind of figure out what we think these 2 things will do. This would be easier if it was an ionic compound. If it was ionic, you would just write both their oxidation states and change it, but it's not, so they're going to kind of share valence electrons. So there's just a couple things we need to avoid. If I just have one of each of these, I have to think about how many valence electrons they have, and if I can make that Lewis structure work. So S has 6, Cl has 7, that would be 13 valence electrons. And that wouldn't work because you can only have even numbers here. So we only draw things in pairs, either bonds or lone pairs. You can't have single electrons. So we know this isn't the answer. So I could try SCl2, which would look something like this. I'd have 2 chlorines. And if I do that, I have 20 electrons to use. And I think that works out nicely. Makes a nice Lewis structure. So I'm going to call that my answer. This one you can also have SCl4 or SCl6 all work out. So any of those would have been right answers. The only thing is it's kind of a weird way to ask this, but you can't have an odd number of electrons. So SCl themselves cannot bond. Type of problem we've seen a bunch this year is this resonance structure. The nitrate ion has been shown to experience resonance when tested experimentally. Draw all the resonance structures. Okay? So this always kind of looks like the same problem. When you're trying to draw the Lewis structure of nitrate, you always end up in a situation where you have to put a double bond somewhere, but you don't know exactly where to put it. So I choose in this first time to put it here. This has 24 electrons, so put my drawing in brackets, and that is a valid Lewis structure for nitrate. But I could have equally chosen to put the double bond here or here also. So I can redraw it where I choose to put the double bond somewhere else. I just added my electrons everywhere else as needed. And I have a third version where I put the double bond at the bottom. Any of those three structures are equally valid. They are considered resonance structures. We can draw the resonance hybrid from those, which is what we would actually experience if we examine this model or this molecule in real life. Is that you wouldn't find that one of the NO bonds is double and two are single. You would instead find that the double bond gets kind of shared equally between each of those three bonds. So you don't actually have, up here, according to your picture, you should have one double bond and two single. But in fact, what you actually end up with is 3 1 1/3 bonds. And they would have properties in between a single and double bond. And this is what you would actually see. All 3 of the NO bonds would have the exact same properties. They'd all be even. And that's called a resonance hybrid. Part C uses that. It says to compare the strengths of the bonds that appear in the resonance hybrid to the strength of a normal NO single bond and NO double bonds. So these bonds are kind of like we said, 1.33 bonds. So the hybrid bonds are stronger and shorter than single bonds. But weaker and longer than N double O double bonds. And that's the idea, is those bonds have properties in between those things. The hybridization of the nitrogen atom, you can use any of these drawings, they're all the same. The hybridization is just how many groups you are bonded to. Okay? 1, 2, 3. So it's sp2. Okay. Quickly with that counts double bonds the same as single bonds. Lone pairs are the same as other bonding things. So some other things that would be sp2, like this would be sp2. Hypothetically, something like this would be sp2, or this would be sp2, or anything like that. So it's just how many things is it bonded to is all you're looking at. And then lastly, what's the molecular geometry of this ion? It's bonded to 3 things and no lone pairs. So that is trigonal planar. So a lot of good review of the different Lewis structure sort of things I can ask you in those. 19. Use intermolecular forces to explain why bromine is a liquid. BRL at room temperature, but chlorine and fluorine, these are all 2s, are gases. Okay. So bromine hasn't boiled yet at room temperature, but these 2 have. So we're going to start by saying bromine has a greater boiling point. That's our first idea here. It's still a liquid, meaning the temperature hasn't been high enough for it to boil. So it boils at a greater temperature than those 2. So bromine has a greater boiling point. So we'll start with that. Okay. Because, and now we have to kind of compare their intermolecular forces. There's no dipole-dipole forces. There's no hydrogen bonds. The only thing these things have are London dispersion forces. And remember, London dispersion forces, the bigger your atom is, or the bigger your molecule is, the more London dispersion forces it has. Okay? So our reason here, bromine has greater boiling point because it has greater London dispersion forces and therefore more intermolecular forces. Okay. And I could elaborate more to make sure I get my points. I could say all three of them only have London dispersion forces and bromines are the highest. But this is a good enough answer for me. And then 20, compare and contrast the structure of metallic and ionic solids to explain how they conduct electricity different. Okay, so I'm just going to do a little sketch. Drawing might help with this. So over here on the left, a metal, you have all of these free floating electrons. Whereas in an ionic solid, you have patterns of positive and negative charges, but everything is locked in place. So what you can say is electrons are free to move in metallic structures, or I should say in metals, so they conduct electricity. Ionic solids have electrons that can't move. Or something along those lines. You could say it has ions that can't move. I did a drawing, but you could also use those keywords instead of doing the drawing. Electrons in a metal metals have a sea of electrons. The electrons are free to move. Ionic solids have a lattice structure, so everything's locked in place. But an explanation like this works just as fine. And on to the last page here. Starting with some gas problems. Calculate the pressure, and it wants us to do it 3 times, once in each of these units. If you have 0.685 moles of an ideal helium gas in a 2.5 liter container, 25 Celsius. So just kind of listing some information. First thing, 25 Celsius. I don't like that. 25 plus 273 to get our Kelvin temperature. Make sure to use that instead. All right, so I'm going to set up the ideal gas law. PV equals nRT. I'm looking for pressure. I have the volume is 2.5. My number of moles is 0.685. Then we get to R. R could be a couple different values depending on which type of pressure you're looking for. For ATM, R will be 0.0821. Millimeters of mercury, it'll be 6236 as R. For kPa, it's 8.31. And that would be on your formula sheet as well. All right, so my pressure over here, let's do ATM first. 0.0821. Temperature, make sure you use the Kelvin, 298. And you will solve it. You can redo the problem for the next unit of pressure. Pressure times 2.5 equals the same moles. This time I'm going to use my 6236 times temperature is 298. And then I'll do the problem one more time. I'll do it up here just to have room. Pressure times 2.5 equals 0.685 times 8.31 times 298. All right, those are my 3 expressions. Now I just need to set up my calculator. So over here on the left, starting here, I'm just going to multiply all this stuff together to simplify it. And then to get P by itself, just divide by that 2.5. P equals 6.70 ATMs. Repeat with these numbers. I get 0.685 times 6236 times 298 divide by 2.5. And this one, I get pressure equals 590 millimeters of mercury. And up here, 0.685 times 8.31 times 298 divided by 2.5. Pressure equals 679 kPa. Same problem, solved with 3 different units. 22. Which of the following molecules would you expect to have a higher root mean square velocity? So we have this weird formula. Root mean square velocity. It's the only time I ever see it show up. This is just a fancy way to say average speed or average velocity. And I have 2 different situations here, and I just want to know which one will have a higher velocity. Okay, so I'm going to do it for both pieces of information here. I have hydrogen gas at 200 Kelvin or nitrogen gas at 2000 Kelvin. Okay, so let's try. Make this first one, this will be hydrogen gas. Okay, so I'm going to plug in everything. 3R is just the gas constant, and we use this 8.31 gas constant always. But if you use the wrong thing, it won't really affect anything. The temperature of hydrogen is 200. Divided by M is molar mass. The molar mass of H2 gas is 2. So 3 times 8.31 times 200 divided by 2. 2493, we take the square root of that. Which gives me 49.9, and our unit is meters per second. And I'll just repeat this calculation for N2. 3 times R, all the same. My temperature this time is 2000. But my molar mass of N2 is 14 times 2 is 28. So see, this one's bigger. We have to do 3 times 8.31 times 2000 divided by 28, square root 42.2 meters per second. All right, so hydrogen is moving faster. Remember, being smaller makes you faster, so that's why the hydrogen's significantly faster, but moving at a higher temperature speeds you up as well. So if I increase the temperature or decrease the molar mass of something, it'll go faster. 23. The boiling points of ethanol and dimethyl ether are provided in our table. Identify the intermolecular force that's responsible for the difference in this boiling point. So we're going to compare these two. It looks like this one has a much higher boiling point, and there must be a reason why. So let's look at intermolecular forces to try to figure it out. What I notice here, they have all the same atoms, but they're arranged differently. The main thing I notice here is ethanol has an O and H bonded. That's a hydrogen bond. There's no hydrogen bonding in the dimethyl ether because the O or the H isn't not attached to the O is attached to C's only. So you can say ethanol has hydrogen bonding. Therefore, it has greater intermolecular forces and a higher boiling point. All right. 24. Compare the vapor pressure of H2O and dimethyl ether, which we have up here. So H2O, we don't have in our thing, but we know H2O. H2O has relatively high intermolecular forces because it has those hydrogen bonds. H is bonded to an N, O, or F. Dimethyl ether does not. Okay, but we're comparing their vapor pressure. Remember, it's how much vapor they make. Things with higher intermolecular forces, like water, make less vapors. Things with weaker intermolecular forces make vapors easier. So when we compare these, we're going to say H2O has lower vapor pressure than dimethyl ether because it has greater intermolecular forces. Or you could explain it backwards. Dimethyl ether has greater vapor pressure because it has lower intermolecular forces. Then 25, explain what chromatography is and how it separates molecules based on their polarities. So we didn't ever get a chance to do our chromatography lab, but we will soon. It says, explain what chromatography is and how it separates molecules based on their polarity. So the main idea of chromatography is that a solvent will travel through a solvent, and we're going to call this the mobile phase, will travel through a medium like paper. It can be other things, but we usually use paper, called the stationary phase. Okay. A dye is placed on the paper and will move with the stationary phase. Move with the mobile phase, the solvent. The more the dye moves, the greater its attraction to the mobile phase. And then the last thing I should probably include is a little bit about polarities, because that's what it says up here. Okay. I'm going to say polar phases attract polar dyes and vice versa. Just so I make sure to include that word in there. And that's it. That should be all the different questions there. Okay. Make sure to go through, make sure this is completely filled out by the time we get back from break on Thursday, January 4th. Unless you're looking at this in the future, it might be a different day. But make sure you have this back in time for break. And let me know if you have any questions. I'll be available by email, but I won't be checking them all the time. So if you have other questions about it, feel free to send me out an email. I'll try to get back to you when I can. Unless it's like the day before we get back, then I'm probably just like, you're on your own a little bit. But, all right, enjoy the rest of your break, and I'll see you soon.